Hello, this is Dr. Marina Sabra from the Lebanese University. This chapter is about binary combinational logic. The outline of the chapter is we are going to begin with binary gates, truth tables, how to implement a logic function, canonical form representation. In the first presentation, I'm going to talk about these topics, and in the second presentation, I'm going to talk about the K-maps and how to reduce logic equations using K-maps. To begin with, we already talked about binary and the binary representation. Now we are going to talk about how to combine them to make a binary function. So basically, we are going to use what we call logic operators, the AND, OR, and NOT. The AND is denoted by a dot, the OR by a plus sign, the NOT by either an over bar, a apostrophe, or a hash before the variable. You have to note that the expression looks the same as addition. So in mathematics, we have 1 plus 1 equal to 2. But in binary, we read it 1 or 1 is 1. And also, we do not have to confuse between the multiplication in mathematics and the ANDing expression in the binary logic. What are truth tables? A truth table is a table where we put all the possible combinations of the different variables inside the function and the outcome of the function. So to begin with, we have the basic truth tables of the AND. For example, in here we have the variables x and y, and z is the combination of x and y, and you can see that z is only true when x and y at the same time are true. Or, so it is x or y, so when either x is true or y is true, you have the output is true. The NOT, so the NOT is just the opposite of x, so you can see it here in the table. So the tables allow us to see the outcome and to test every value that you have. How to implement this? So the first kind of implementation is going to be in switches. To implement, a logic 1 is a switch which is closed, a logic 0 is a switch which is open. Therefore, in the output side, a logic 1 is an output is on. Here we called it a light, so I put a light bulb on the output. A logic 0 is a light which is off. And NOT is inverted, so if the switch is closed for a logic 1, therefore current is passing in here. For logic 1, switch is open. So you have here some applications. So to create a circuit, an electronic circuit that would do the OR expression, I have to put them in parallel so that if the switch 1 is closed or switch 2 is closed, the current passes from the source and gets into the output. At the same time, AND is two switches that are in series, and a NOT is a normally closed switch. This means that if C is equal to 0, the normal state of the switch is closed and it passes the current, giving it an open, on light bulb. And if C is equal to 1, therefore I give it current, and here it opens and it cuts the current from the output. So it works inversely with respect to its own value. To implement a logic function, it means you have to combine different values, different states of the output inputs to create a condition for the output. So in here, if series is AND parallel is OR, you can assume or you can evaluate the expression to say that it is A and either this expression or this expression are true. So we get A and B and C bar or D, of course between parentheses, so that they all combine with the condition A. Logic gates. So to represent these, we either use the switches or we use logic gates. In the PLC applications, we are going to use the switch logic. The logic gates are a different but a very well used standard in logic expressions. So to begin with, this is the representation of the AND gate, the OR gate, and the NOT gate. The NOT gate is a combination of the NOT, which is the bubble, and a buffer. A buffer in electronics is something that does nothing logically, but it gives energy only. So this is the NOT for the gate. So in waveform, this means that if this is x and this is y, this is in a timeline, so it changes with time, x and y. So the same thing that you have seen in the truth table, you can see it also here in the timeline, where x and y is only true where x and y are both true. X or y is true anytime any one of them is true, and not x is the opposite of x. And it is important to know how to see the results in these two different ways. If I have more than two inputs, for example, in here I have 3 inputs, I can have 3 inputs to an AND gate, I can have multiple inputs in here to an OR gate. We are not restricted only to these 3 basic gates. I can name in here, for example, an AND gate, which is an AND gate combined with, with the bubble, which is the NOT. This is why I explained that the NOT is only this. The NOR. We also have the exclusive OR, which is XY bar or X bar Y, which is true only if one of them is different than the other. It is false whenever both of them are the same. Exclusive NOR, which is the opposite of exclusive OR, which is true when X and Y have the same value, and false when X and Y are different. For now, we are only going to learn how to use these 3 to create logic functions or logic diagrams. So we have seen how to represent a function in the form of a truth table, and in here I have a truth table where I don't know the function. I have to I can take the function from the truth table. I can, from the function in here, create the truth table. So if I want to begin from this, f is true whenever x is true, so I go to all the states where x is true, and I can put f is true. It is also true when y is 0 and z is equal to 1. So I go where y is 0 and z is equal to 1, and I add value true. And here it is already covered by the fact that x is true. So this is the expression that I have in here. It's another way to represent the function. A third way to represent the function is the logic diagram. So the logic diagram is a straightforward expression of the equation that I have. So it is x or, this is the or, so whenever I have a value that is in the expression and I see it first, it is the outermost logic gate, and then I have y bar, so it's the opposite, and z. So the note at the bottom says that truth tables are unique. I cannot have for the same function 2 different truth tables. So to verify a function, and if 2 functions are the same, I go for the truth table. Whereas the same function, the same truth table, can be expressed by different equations, and therefore different logic diagrams implemented. So the logic diagram is what we could implement in a logic circuit. These gates can be both as ICs and implemented in a logic circuit. Boolean algebra is a way to mathematically, in the expression form, reduce the expressions, because if I want to go for a very large expression, if I go back to the previous slide, you can see if the expression is large, the logic circuit is going to be big. So therefore I have to reduce it. The theoretical way, or the expression way, is using Boolean algebra. So we are not going to go through this method in this course. We are only going to learn just the basics, and we are going to use k-maps to reduce the expressions. So if I go for example, in here, x or 0, so if I or 0 with any variable, is going to be this variable. X or 1 is always 1. You can test it in the truth table. X or x is x. X or x bar, so whenever x is 0, x bar is 1, so it's going to be ORing, so it's going to be 1 all the time. The not of x is x itself. If I want to go for the ANDing, x and 1 is x, so it's just the opposite in here. X and 0 is 0, x and x is x itself, and x and x bar is 0, so it can never be true itself and its opposite at the same time. Some basic laws that I would like to mention in here: x or y equals to y or x, same for the ANDing, this is the commutative. X or y or z is equal to x or y or z when we change the expression that we solve first. This is the associative property, also true for the ANDing. The distributive as well, so x and y or z is x, y or x, z. Same for the complementary equation. And the law that also is most used, De Morgan's law, is the not of the whole expression x or y is not x and not y. So we not only do the opposite of the variables, but also of the expression. And also the not of x and y is x, not x or not y. I will stop on these. We have in here an example on De Morgan's law. So if we want to complement, take the opposite of an expression, like f is equal to x bar y z bar, or x y bar z bar, it is going to be x or y bar or z. So I inverse the value of the variable and of the or and. So if I want to complement this expression, what does it become? Again, every or I'm going to change it to and, every and to an or, and the variables themselves are going to switch states. The Boolean operator precedence is just like the arithmetic, so we have a first priority on parentheses, then the not, then the and finally the or. Boolean function evaluation. So in here we have an application. We have 4 functions. We have on the table implemented the first 2, and we expect that you do the 2 others. So explain the first one, x, y, z bar. So every time x and y are equal to 1 and z bar is equal to 0, this is the function is equal to 1. Because I only have one term and the term contains all the variables, you can see that in the truth table I only have one term which gives the function equal to 1, and every other combination gives the function equal to 0. This is what we later on are going to call a minterm. In the second expression, the variables or each term in here in the sum of products form doesn't have all the variables inside it, so it is not a minterm. So x itself takes 4 different possibilities. So whenever x is equal to 1, that means all these 4 cases the function is equal to 1. And whenever y is equal to 0 and z is equal to 1, this is the other case. You can also take these. This is going to be 1 term, 2 terms, and this one covers 2 other terms. Some of them could be overlapping with other available terms. So I have here a function which is a function of x, y, and z, and it is implemented in its form, in its actual form. The question is to simplify and implement so that we can compare between when I implement a function as it is and when I simplify it, and to see the importance of simplification in the reduction of the expression. In here, x bar yz or x bar yz bar, so we have in here the implementation in nots, in ands, and in ors. Of course, if I have x bar twice, I am going to put one not gate and use it in a combination for the inputs of the two other gates. So I expect that you do the answer, you do the solution of this expression, and I will give you the answers later on. You have to note that in here you have to take x bar y into common and then continue. What about canonical forms? Canonical forms are the min-term or what we call the max-term form. They are standard representations. We are going to talk about them now. They allow to test the truth or the equivalence of two binary equations, just like the truth table. Their implementation is on a two-level logic circuit. This means we have two rows of logic gates. The logic equation is always a sum of products in the case of min-terms or a product of sums in the case of max terms. No other combinations. I'm sorry. So we are going to define both of them, but later on we are only going to work on the min-terms because it is the same. The same method is either min-terms or max terms. So each min-term or max term corresponds to exactly one line in the truth table. The min-term is the product of the variables in the truth table. The max term is the sum of the complements of the variables. The index that we have in here is the order of the term. So in a truth table or in a min-term max term form, it is always very important to put them in order. So we begin in alphabetical order and we begin counting from a value of binary equivalent 0, 1, 2, and so on. So in here, the min-term equivalent is what makes this value or the function of the truth table equal to 1. So this is x bar, y bar. The max term corresponding to it is x or y. And this one is x bar y, xy bar, and xy for the min-terms. And it is x or y bar, x bar or y, x bar or y bar. So the max terms are exactly the opposite in the Morgan's law with respect to the min-terms. So when you talk about the standard order, we are talking about the order in which we have to list the min-terms so that we can compare them together. And it is a convention, so we have to abide by it. So if I have values and we choose that they are in alphabetical order, this is what we use. So these are terms that are correct, and terms like this, even though they give the exact same value, are not in the standard order. Therefore, when you talk about min-term form, they are, or in here it's a max term, they are not accepted. And another condition is that in here I have a term, if the function is a function of ABC, so a term BC bar doesn't contain all the variables, so therefore it is not a min-term. So another example, in here we have some values of a 4-variable table. So I have the index of 0, 1, 3, 5, 7, 10, 13, 15. We have the binary equivalent, and you have the min-term and the max term. So I will stop this video in here, and the rest I'm going to do them in the separate video.